All right, and so now we're looking at the product property of some general nth root right here. So let's see what we have on the computer screen. For square root, we had a product property as following. Taking the square root of a product a times b can be equal to the square root of a individually multiplied with the square root of b individually. So this product property here is for square root. And the same product property for square root, we had a revised version that says anytime we're having the product of two square roots, we can combine it into one square root of the product a times b. And so that product property we have seen now can be generalized into the product property for some general nth root right here. So this is how it says right here. So let's say n be an integer greater than or equal to 2. And then anytime the nth root of a and the nth root of b are generally defined, meaning having real value that we can compute with nth root of a and nth root of b, then it's going to be true that we have the nth root of the product a times b will equal to the nth root of the product of a, the nth root of a in product with the nth root of b. And then vice versa, sort of like the revised version of the square root product property. Then here we have on the revised version, like that, the backward version, the product of the nth root of a with the nth root of b can be written or combined as one nth root of the product a times b. All right, and so now after looking at the product property for a generalized n root like that, and where we have seen some generality and some similarity with the product property when we were studying about the square root here, then let's see how we can apply and let's learn about how we can apply the square root the product property of a general n root into a problem right here. So I call this a problem because I want to demonstrate the idea of how we can utilize, and then after demonstrating the idea, we're going to formulate into a solid technique right here. Okay, and so the instruction of this problem here is asking us to reduce the following. It's a cube root of 3,645. 3,645. Okay, and so once again, it's a very big, large number inside a cube root, and clearly 3,645 is not a perfect cube. Okay, because the only method we know so far is anytime we're taking an nth root, say for example right here as a cube root, then we try to see how we can express our value here as a perfect cube or a perfect nth power. But sadly, it's not. 3,645 is not a perfect cube. Okay, so how can we, and that's the reason why you can see the intention of the problem here is we are asked to just simply reduce the square root. Okay, and so now after some of that explanation right here, allow me to bring in the following. Here's my observation about this problem. 3,645 inside of the cube root right here, and we can hopefully see this as a generality for some general nth root right here. Now prime factorization, and we don't have to go all the way down to listing down all the primes, but I already observed that this value right here has the ending digit here being a 5. That means it has to have 5 as a prime factor. So again, I repeat simply as an observation, I can see that 3,645 has the ending digit here being a 5. So that rings a bell for me, and that's just common math right here. That it rings a bell for me that this 3,645 must have 5 as a prime factor. So in that way, I can now go ahead and rewrite it as, so 3,645 as a product of 5 times, and the other value is 729. The other value is 729. Okay, and so 729 from some of the earlier problems that I have demonstrated, then 729 right here can be expressed as, so just that value right here can be expressed as a 3 to the 6th power. And then now the other prime factor is here. So now I have completely put my value 3,645 into a product of prime factors. And so I have completed the prime factorization. Okay, and then what I said earlier about we didn't have to go all the way down is because for this problem right here, I saved some effort by using some of the values we already had, the prime factorization from the earlier problem. And then so in the other problems right here, that we have to go all the way down to the complete prime factorization process. Okay, and so now for this problem, so with that little thought right here, right, that I have right here, writing my 3645 as the prime, as a product of the prime factors with some powers included. And so now I can rewrite that here as cube root of 3 to the 6th power times 5 here. Let me leave that out on a separate space. And so now in my next step, the product property we have just learned allows me to turn this, so what I see here is a cube root or some general n root of a product between some two factors here. So now I can write it as one separate cube root for 3 to the 6th, and another separate cube root for 5. Right? And so now this cube root of 5 right here, since 5 is a prime factor itself and no special power, it's just power 1. So cube root of 5 is irreducible right here. Okay, so that means we're going to leave that in exact expression. Now, we have learned from earlier problems and examples, 3 to the 6th, at least this prime factor is being written as a power being a multiple of 3. Our root here is a cube root, third order. So our value here is a 3 raised to a multiple of 3, matching with that. And so I'm seeing that here from previous problems. Now I can see that as cube root of 3 square cubed times cube root of 5. And that's, I just decided to give extra clarification. But so the final answer comes out, right? Cube root of 3 square cubed right here gives me really a 9 right there. So 9 times cube root of 5. Our answer here, since the cube root of 5 here is already explained to be an irreducible one, and the 9 here is the final outcome of taking the cube root of 3 to the 6th, or taking the cube root of 3 square cubed right there. So we came out with a 9. So our final answer here is expressed as a 9 cube root of 5. And that's how we're doing this problem right here. So the product property was utilized right here, so that we can, at least the point now is that we have reduced we still have some leftover value being trapped, being put inside the root, but the amount of value right here is already a lot reduced right here, and it's no longer can be reduced any further. So we write it in the exact expression, and then we leave that 9 out in front. Okay, so it's 9 times the cube root of 5, and that's how we have reduced the root expression right here. But so generally, what we used here is we use the product property. The product property allows us to break that down and separate that into an irreducible root and a reducible root right here. Okay. All right, and now let's look at part B of this demonstration problem number 4 right here. And I want to, once again, introduce how we can use the product property into reducing a root where we have variables, lots of variables involved right here. Okay. So what I'm seeing here is 1280 in product with x to the 9th in product with y to the 11th. The entire product here is being inside of the 4th root. So we're taking the 4th root of the entire expression here. Okay, and so quickly as an observation, 1280 is not a perfect 4th power. That's so clear. Okay. The x to the 9, the other prime factor is also, so this is that power right there, right? Is not a power multiple of 4. And so in order to reduce this, each of these power need to be a multiple of 4. Okay, because it's a 4th root right here. But so now, sadly, this x to the 9th, the power 9th, is not a power being a multiple of 4. Similarly, the same way that happens with the y to the 11th, this power 11 is not a power that's being a multiple of 4. So in that way, we're in the, how are we going to reduce something like this? So now to tackle this down, I'm going to go from the 1280. In prime factorization, 1280 comes out being 2 to the 8th power times 5. Okay, and then precisely how I carry through the prime factorization process, then check out my other video lessons for showing how to do this, or they have this kind of resource all over the web in these days. Okay, so at least what I recognize now is that as a product of prime factors, this 1280 has prime factor of 2 to a power being a multiple of 4. This other one is not. Okay, keep that in mind. Now, the x to the 9th being part of the entire expression inside my root, the x to the 9th, the power here is a 9. It's not a multiple. Clearly, this power is not a multiple of 4. But being a variable, here's my trick right here. I'm going to look for the largest. I'm going to look for the largest multiple of 4. That's less than 9. The largest multiple of 4, less than 9. Okay. So here, that largest multiple of 4, less than 9, it's going to have to be 8. So I'm going to look at this as x to the 8th times x to the first power. And all of that here is x to the 9th. So once again, my thinking process is that my reasoning was that this 9 right here initially is not a multiple of 4. This power 9 is not a multiple of 4. So what I did there was I looked for the largest multiple of 4 that's less than 9. And that in our mental math skill is good enough to recognize that the largest multiple of 4 less than 9 has to be an 8. So now I'm going to re-express x to the 9th as x to the 8th times x. This is to the first power. Okay. And so in that same way, the y to the 11th, this power 11, once again, is not a multiple of 4. So I'm going to look for the largest multiple of 4 less than 11. So the largest multiple of 4 less than 11 has to be the power 8. So I'm expressing y to the 11 as y to the 8 times a y cubed. All right. And so after this breaking down right here, here's my prime factorization of the 1280, the numerical part of that. The x to the 8 times x is my re-expression of x to the 9th. I purposely display that as a product between, a power being a multiple of 4, right? And then times x right here. And like I said, the trick here is this is the largest multiple of 4 less than that value. Okay. And so now in this way right here, the entire 1280 x to the 9th y to the 11 can be re-expressed, and this is, once again, realize that this is the expression inside of our fourth root, can be re-expressed as 2 to the 8 times 5, that's for 1280, times, in product with, now x to the 9th is x to the 8 times x, and then the y to the 11 times y to the 8 times y cubed. Yes, it does look lengthy a little bit, but it will get a lot better. Okay, and so now I'm going to bring this result and come back to the other board. So now back to the original problem. My next step would be to rewrite the entire expression inside the roots to be like what we have seen on the other board right there. So now it's 2 to the 8 times 5 times x to the 8th times x times y to the 8th times y cubed. And then after that product, we take the fourth root. Okay. Yes, I admit it may be a little lengthy for now learning at first, but it will get faster as we get comfortable with that. But it's all about, we recognize, we all due to that, the fact that our root here is the fourth root, so we recognize as much as we can the largest powers being multiple of 4. Okay, the largest multiple of 4 powers among all of these values as prime factors. So now that's a power multiple of 4. That's another power being the multiple of 4, and that's another power multiple of 4. So now I'm going to rearrange them. It's better to rearrange them. So the fourth root right here, okay, we have 2 to the 8 times x to the 8 times y to the 8, and then all of these remaining powers no longer powers multiple of 4. I'm going to regroup them. So now I have in products with 5x y cubed. All right. And so now you can see further that this power 8 right here is a 2 multiple of 4. This power 8 is also a 2 multiple of 4. This power 8 is also a 2 multiple of 4. So in that way, my next step right here, that's 2 to the 8 is understood as 2 square to the 4th power. That x to the 8 is x square to the 4th power. That y to the 8 is y square to the 4th power. These are all multiplied together. And then continuing inside our root right here, we got 5x y cubed. All right. And so now one more step. I'm seeing that now we have all displaying power of 4, power of 4, and power of 4. So inside of the fourth root, now I have 2 squared is a 4. 2 squared is a 4. I have 4x squared, y squared, all to the 4th power. And then in product with the 5x y cubed. So that's how I've made my way from 1280x to the 9th, y to the 11th, right? To re-express it as a product between 4x squared, y squared, all to the 4th power, and 5x y cubed. That product is inside the fourth root. So now with the property we have just learned right there, now I can rewrite it as fourth root of 4x squared, y squared, all to the 4th, times the fourth root of 5xy cubed. And so now at this point right here, after using the product property, I have now isolated out, and what I see here is the fourth root of some expression to the 4th power. So that now will become in my next step. So with that step from the other board right here. So my next step now is going to come out with now 4x squared, y squared, no more 4th power and no more the 4th root. All of that here is in product with the 4th root of 5xy cubed. And this part right here is now completely irreducible. And so my final expression comes out. The final reduced root that we have here is going to be 4x squared, y squared in product with the 4th root of 5x y cubed. And that's how we have reduced the large root that was started from here, the large root with the high order, and then we reduce it down to 4x squared, y squared, multiplied with 4th root of 5x y cubed right there. And so this is very irreducible at this point. Okay. All right. And so now we're going to apply that generality we have seen right there. Basically, when it's variables raised to some power and the power itself does not appear to be a multiple, some multiple of the root order right here, then we're going to have to find the largest multiple, in this case 5, the largest multiple of 5 less than 8 for that power n, largest multiple of 5, okay, less than 12 for that m right here. And then we're going to have to do some prime factorization to find the largest, the power being a multiple of 5 in this 160. And that's the process right there. Okay, and so now on scratch work, 160 is the same as 5 times 2 to the 5th. Okay, and this is the complete prime factorization of 160. And how I got that so quickly, once again, check out some learning resources about showing you how to find a prime factorization like that. Okay, so the next part I had n to the 8. This power is not a multiple of 5 clearly, but the largest multiple of 5 less than 8 is going to be a 5. So I'm going to re-express that as a n to the 5th times n cubed. Okay. The next one, m to the 12. Clearly, this power of the m right here is not a multiple of 5 clearly. So the largest multiple of 5 less than 12 will be 10. And so here I'm looking at m to the 10th times m squared. And so now with these prime factorization for each of our components here, the entire 160 n to the 8 m to the 12 right here can be re-expressed as the product of 2 to the 5th times 5. That takes care of 160 times the n to the 8 now becomes n to the 5th times n cubed. Okay, and then the m to the 12 here becomes the product of m to the 10th times m squared like that. All right, so that's now my scratch work. So now back on my board right here. In the next step, I will write it as the following. 160 inside of the 5th root, 2 to the 5th times 5. The n to the 8th inside the 5th root times n to the 5th times n cubed. The m to the 12th inside the 5th root, m to the 10th times m squared. And the entire product here is put inside the 5th root. And then so just like that generality, once we have recognized all of those, and we did the best we can right here for all of those powers being multiple of 5 right here. So now I'm going to rearrange them so that all of those powers, those prime powers of multiple of 5 can be grouped together. So 2 to the 5th times n to the 5th times m to the 10th, and times, and group that together, and times with 5n cubed m squared. And that entire product is being placed inside of our 5th root. And so now one further explanation, and one day I hope I can skip this step right here, because when you become fast enough with the powers, I can skip that step. But this is 2 to the 5th, this is n to the 5th. 10 here is a 2 multiple of 5. So that means in the next step, I can rewrite that group here as 2 to the 5th times n to the 5th times m squared to the 5th. So now we're displaying all of the 5th power and 5th power like that. And then in product with 5n cubed m squared like that. And then this is all inside the 5th root. Okay, and so now in the next step, yes, now I can combine it all into one power. So the 5th root, the inside of that, we're having 2n and m squared, all to the 5th power. See, 2n and m squared, 2n m squared. All of that is one combined 5th power. And it is in product with 5n cubed m squared. And so now we have expressed our beginning expression here as a product of these two factors. But now this first factor here has been displayed as a power of 5 right here. And so that matches with this. And so now using the product property, I can turn that into the 5th root of the 2n m squared all to the 5th power multiply with the fifth root of 5n cubed m squared. And so that fifth power will be reduced by that fifth root right here. And so in my next step, we're looking at 2n m squared. No more power, no more roots. And then we're multiplying that with the irreducible roots. Fifth root of 5n cubed m squared. And that's how we have completed our problem. All right, so let's look at example number 7 right here. And in this example number 7, it's quite straightforward how I will apply the product property, but the opposite direction right there. In a sense that I am going to combine two separate cube roots or two separate n roots into one n root. And let's see how useful that can be for some of our situation. But the most direct application here is we can just simply, from two separate roots, what it says here is a cube root of the 25x to the fourth y multiplied with a cube root in products with another cube root expression, cube root of 5x squared y to the fifth. Okay, and so now straight out from the product property, we can combine this into one cube root. The cube root of the product between 25x to the fourth y and the 5x squared y to the fifth. Okay, so I just directly utilize the product property. And so now in that way right here, I can proceed a little further. Now since both factors, big factors of this large product here stays inside the root, I can start multiplying them numbers with number in the usual algebra sense and variables with variables. And so in that way, I'm looking at 25 times 5 gives me a final coefficient, 125. X to the fourth times x squared gives me a final x to the sixth power. Y to the first power times y to the fifth gives me a final y to the sixth power. That entire shortened down expression is being placed inside a cube root. And now with all of that experience we have learned prior to this example, once again, let's look for any one of these, right? The numbers, the power, the variables with some powers. Let's look for those powers being multiple of 3 here, because our root here is cube root. Okay, and so I can easily see 125 is easy enough to see that it's the cube of 5, the perfect cube of 5. X to the 6 here is already itself a multiple of 3. And so we don't need to look for the largest multiple of 3 less than 6. That's x to the power 6 itself is already a multiple of 3. So I'm seeing that here as x square cube because it's a 2 multiple of 3. The y to the 6 here, I'm seeing that as y square cubed. And so now the entire expression here has become, inside of the cube root, we're looking at 5x squared y squared all cubed. And we take the final cube root. And now with this final cube root on a perfect cube right here, we utilize that understanding we've seen earlier. Then it will, see the cube roots reduce into that power 3. Okay? Now that becomes 5x squared y squared. And that's now simplified our expression right there. So from something that has product, lots of product, and cube roots all over, now we came down to something just a lot simpler. And that's how we have simplified this. And the essential theme right here, we use the product property, the backward direction right there. Okay. All right, so allow me to bring in a little problem right here, but it does come up with some good generality for us here. Let's say here I'm using fourth root. Let's say we have, according to the order of operation, fourth root of x, and then we raise that, whatever that will be, to the fourth power. So I purposely raised to that power being exactly the same with the order of our root here. So fourth root of x, after that raised to the fourth power. And then since the x itself right here is being placed inside an even root, so from our previous understanding, so the x got to be a non-negative value greater than or equal to 0. But the point is the fourth root of x here is a defined value. It's a value that has real number, real value in the end. That's what it means by being defined. But the idea is, so let's find out what we can do with fourth root of x and raised to the fourth power. Okay, so that means fourth root of x times fourth root of x times the fourth root of x, okay, for whatever x value is, as long as x is a positive or, positive or 0, multiply with fourth root of x. And now the product property we have previously learned allows us to combine all of these into one fourth root. So one fourth root, we're looking at x times x times x times x. And that will essentially make that as the fourth root of x to the fourth. Okay, and so now from that property that we've learned right here, and it's been what we've been doing right here. Now x is a non-negative number, and then it's an even root, but then we take the root of that exact same power right here, fourth root on the x to the fourth power. So the answer has to come out exactly x, like that. Okay, the answer for this problem came out exactly x, like that. But what we noticed from the beginning right here, we got some general nth root, and we raised that nth root to power n. Okay, and then the requirements here is because it was an even root, but we're talking about now, generally speaking, it's for any x values that making the nth root defined. Okay, and so now what's that generality we can see here? Let's turn over to the computer screen. All right, so on the computer screen, what I see here is, as long as nth root of a is a defined value, then raising the nth root of a to the power n will come out exactly equals to the nth root of a to the n, and which ultimately at the end equals a. So that was just how I explained it here, starting with the fourth root of x all to the fourth. I made my way and through the product property and came down to, see, now it looks like the fourth power got swapped and became inside of the root. And now ultimately it all came out to the final value x right there. Okay. The generality we just learned right there is allowing us, from this point on, you will hear a lot of people say, for example, okay, so with this problem right here, part A of the example 8, we are asked to raise the fifth root of 15 to the fifth power. Okay, but now the answer comes out with just simply as simple as just 15. And so you may have heard, or you will start hearing people saying that from this point on, that the fifth power cancel with the fifth root, or the fifth root is canceled with the fifth power, basically raising to a power that's matching with the order of your root. It will cancel the operation, so we don't need to go through the lengthy calculation anymore, and that simply come out just that number of 15. We utilize directly that property we've had. And so I may not get to this point back in the lessons about square root, but now we can also clear it up. All right, part B of the example, square root of 3 all square. Now the answer can just come straight forward, 3, because square root of 3 now being squared, the square will cancel with the square root, and that's the property, that's the one generalized understanding that we're allowed it to start using from now on. So the square matching with that square root, so the square cancel the square root, making it the answer remains just 3. Just like that earlier, the fifth power of the fifth root cancel each other, so the answer comes out just 15. All right, and so now we're getting into the quotient property of some general nth root right here. Allow me to swing over to the computer screen. All right, so just like back in the lessons for square root of a fraction or of a quotient can be done as the quotient of two square roots. So square root of a over b can be equal to square root of a divided by square root of b, as long as b is a quantity that's positive. Okay, and so same way, this quotient property on square roots, as a revised version, we can go from the quotient of two square roots, square root a over the square root of b, can be equal into a one combined square root a over b. And so now we can generalize that into one quotient property for some general nth root. So n has to be an integer greater than or equal to 2. And then as long as our n root of a and n root of b are all defined value, and we must make sure that the b, because in this work right here we're putting b in the denominator, so make sure that b is a non-zero quantity. Okay, then it's true that the nth root of the fraction a over b can be calculated as the quotient of the nth root of a over the nth root of b, or vice versa. When you have a quotient of an nth root of a over an nth root of b, we can calculate that as one general combined nth root of the fraction of the quotient a over b. All right. So in that way, allow me to bring in one example where I can show how the quotient property of nth root can be applied here, can be utilized here. So what I have here in example 9, we want to simplify the cube root of this quotient inside. Okay, and so utilizing the quotient property that we have learned, I can make that into the quotient of one separate cube root for 64 x to the 6, and I can put that as a quotient over another cube root of y to the 9th z cubed. So now we have two separate cube roots to handle, and once we found their reduced answer, then we can put them in a quotient and continue to work further. So now getting it down to each of these, it looks now, even though we have to handle two cube roots, but each of the cube root here is easier to handle over here. So from the previous problems and the experience we've learned from previous examples and problems right here, 64x to the 6, that is a perfect cube of 4. That is a power being a multiple of 3. So I can write it as 4x squared all cubed. And then allow me to start speeding up the process a little bit. And then the explanation can be similar to those of how I've done in the earlier problems like that. As a quotient with now the cube root in the denominator, these powers are gladly all multiples of 3 right here. So the cube root in the denominator, inside of that I can write it as, so this is y to the 3rd power all cubed. Okay, so y to the 3rd, z cubed right here. So I have a z right here, and now it's 1 general power 3. So now in the numerator I have cube root of a 3rd power of 4x squared. So after taking cube root, it becomes a 4x squared. Okay, and then in quotient with, now again we're taking the cube root of a perfect cube power of that entire expression, y cubed z, and so now that becomes a y cubed z, and this final fraction right here, this final rational expression is at its reduced form. And so mainly what I did here is that I turned that into a quotient of two separate roots, where it made it easier to handle each one of these separately, to find the cube root of each one of these expressions. Okay. All right, so in example 10, allow me to demonstrate how we can use the quotient property into another simplification problem here. So what we're asked to do here is to simplify a quotient of 4th root of all that here divided by a 4th root of 5p squared q cubed. Okay, and so to have a little bit of the development on this problem right here, you can think about none of these factors has a power being a multiple of 4. So the power 10 is not a multiple of 4. The power on the q right here is not a multiple of 4. And the 80 right here is not a perfect 4th power. Same way with these in the denominators right here. And the most direct route I can go right now. And at this point there are many different ways of approaching the problem, but allow me to go with the most direct direction, meaning the least amount of steps like that. Using the quotient property, I can combine that into one quotient. So now I have 80 p to the 10 q to the 19 over 5 p squared q cubed. That entire quotient now is being placed inside one combined fourth root. Okay, so now at this point right here, order of operation is saying that we can start doing the division inside of the root right here. So let's do some simplification. 80 divided by 5 gives me 16. P to the 10th divided by p squared gives me p to the 8th. Q to the 19 divided by q cubed gives me q to the 16. And that entire product is placed inside the fourth root, or we're taking the fourth root of that entire product. But see, this product came out after reducing that fraction. And the fraction came out from combining the two little separate roots into one combined root of that entire quotient. Okay, and so needless to say, I was using the quotient property in the backward direction like that. And so now in this way, what I'm seeing is the 16 right here is a 2 to the 4th power. The p to the 8 right here, that power 8 right here is already a 2 multiple of 4. This q to the 16, the power 16 is also a multiple of 4. It's the 4 multiple of 4. Okay. So now we can write this as 16 is a 2 to the 4th power. 2 to the 4th power. The p to the 8 is a p square to the 4th power. And the q to the 16 is a q to the 4th power to the 4th power. And we're taking all that inside of a fourth root. Okay. And now I'm going to combine all of these power 4 into one power 4. So fourth root of 2 p squared q to the 4th power. And so now fourth root of a 4th power expression, that will come out 2 p squared q to the 4th. And that is now completely free from the roots, and we are done simplifying our the expression. And now we're looking at addition and subtraction with general nth roots here. Okay, so let me bring in a problem as following. Okay, so what we have here is cube root of 5 plus the fourth root of 3. The cube root of 5 plus the fourth root of 3. So with a problem like this, then I have to say, let me remind anyone watching the lesson here, cube root of 5 is already irreducible. Irreducible. The same with the fourth root of 3. Irreducible. So that's something we noticed, we observed about these two. And then from our understanding previously right there, then when we have roots, general nth root now being involved together with addition or subtraction, then we must do the roots before the addition or subtraction. So in that case, since each of these roots is already irreducible, we really, whatever value for this root, we will add to the whatever value that came out from that root. But so in what I said earlier, these two roots are already irreducible. Unless we are going with decimals, values. But most of the time we're trying to avoid decimal values. So this, with an irreducible root expression like this, we leave them in exact expression in the way it is. And so in other words, as an exact expression, what we're looking at here is already at its dead end right here. There's nothing else we can do about it. I agree. So we won't be able to do any more rather than just leaving it like this in exact expression, unless we want decimal value. Okay? But allow me now to bring in the following observation. Let's say we have the fourth root of 80. This fourth root of 80 can be reduced down. Now in our experience up to this point, fourth root of 80 can be expressed as a product of 16 and 5. So we've learned all of that property right there, so we can reduce this thing just fine to fourth root of 16 times the fourth root of 5. The fourth root of 5 is irreducible. Fourth root of 16 is the same as the fourth root of 2 to the 4th power, okay, times fourth root of 5. And that's making it all, so fourth root of 2 to the 4th power giving me 2. So my final work here is 2 times the fourth root of 5. 2 fourth root of 5. Okay, So in the way how I'm seeing it now, it means 2 times the fourth root of 5, and the fourth root of 5 is an irreducible value, is an irreducible fourth root, multiplying with 2. So unless we want decimals, which we've been avoiding, this is already, again, it's most dead-end expression as exact expression. But on the other hand, the way how I'm seeing it, so we got the 2 fourth root of 5 out of the simplification work of fourth root of 80. But now if we're looking at the 2 fourth root of 5 a little more closely right here, in the way I'm seeing it, of course we can't multiply any further, right? Unless we want decimal values. But now what I'm trying to express now is that the 2 times the fourth root of 5 means you can do it like this. A fourth root of 5, 1 irreducible fourth root of 5 plus 1 irreducible fourth root of 5. So now I'm seeing 2 like terms, fourth root of 5s added together, and that come up to 2 times the fourth root of 5. Okay? Or you can see that as a 3 times of the fourth root of 5. Take away 1 time of the fourth root of 5 right here. So subtraction between some 2 like terms here, we also arrive at the 2 fourth root of 5. So that gives rise to, hey, wait a minute, a lot of time when the 2 roots are exactly like term, and now be careful, it got to be exactly the same kind of root and the same number inside the root. When they are like roots, like that, the terminologies I'm using here, when they are like roots, then yes, we can combine them just like combining like terms. Okay? All right, so now in a demonstration problem, I call that problem number 6 right here, we are asked to reduce 3 fourth root of 5 plus 2 fourth root of 5. So the way how it says here, 3 times of the fourth root of 5 plus 2 times of the fourth root of 5. Okay, so in that way, just like how I mentioned it in the earlier discussion right there, just right before I got into the problem 6 right here, then that means now I recognize the fourth root of 5 here and the fourth root of 5 there. These two now are like terms. And so now it makes perfect sense that, hey, 3 times of that quantity, whatever it is, plus with 2 times of the exact same quantity. It makes perfect sense without any fancy math. It got to be 5 times the fourth root of 5. Okay, so that's one way of how we can see it. Or a little more mathematically into the explanation. Think about this fourth root of 5 expression and the other fourth root of 5 expression as a common factor. And so according to the distributive law, we can rewrite that here as in parentheses, we can add the 3 and the 2 together, these coefficients. And we multiply with that common factor, fourth root of 5. And 3 plus 2 results in 5 here. That's how we ended up with 5 fourth root of 5 here. And so once again, I did this by recognizing the 2 terms here as like terms. They are like terms in the sense that they have some coefficient, with the core value right here being the fourth root of 5 and fourth root of 5. That's how they are like terms. And then it could have been a subtraction problem right here as well. And then we do that in the same way. All right, so in this problem right here, I want to mention, I've been using the term like terms and like terms, but now if we're looking at this problem here a little more closely, part B of problem 6 right here, these two are not really like terms. Yes, they have same roots, but they are not having the same number right here. So these two are not like terms. So in other words, this is already irreducible. This is irreducible. And this is also irreducible. All right. So now these two, this expression, in other words, it stays the way it is. 8 times the fifth root of 3 minus 2 times the fifth root of 2. And that is already in its most reduced form right there. And that is in the exact expression. All right, so now we are in example 11 right here, where we apply what we have learned previously into simplifying an expression like this. So what I see in this expression here is, regardless of what x is, but we have fourth root of x, fourth root of x. This is 5 fourth root of x minus fourth root of x. And so these two are exactly like terms here. And so now the simplification can be done quite simple. 5 times of that term minus 1 time of that term right there. And these two are really like terms, the same variable x, the fourth root. So now that's yielding 4 times the fourth root of x. That is our answer right here. Mathematically speaking, we can think of that as, since we recognize a common factor of fourth root of x and fourth root of x throughout the two terms right here, distributive law says we can group 5 minus 1. See, this is the coefficient 1. 5 minus 1 times the fourth root of x. And then 5 minus 1 gives me a 4. So we have 4 times the fourth root of x. And so once again, it just reinforced that idea that we're working when it comes to adding or subtracting root right here, as long as the root are like root right here. Exactly like root, or then we're treating them as like terms and we're combining like terms. All right, so now in part B of our example over here, example 11, we're asked to simplify cube root of xy squared plus 4 cube root of xy squared. And so now once again, looking through the entire expression right here, I recognize that we have like terms right here. It's cube root, cube root. Inside of the cube root, we have the same expression, xy squared, xy squared. So these two root terms are like terms. The only difference between them, this term here has a coefficient 4, this term here has a coefficient 1. And so now adding, combining, or simplifying this is going to be quite simple. 4 times of that expression plus 1 time of that same exact expression is making it 5 times of the cube root of xy squared. And that is going to be our final answer. Now, mathematically, a little bit more for the explanation. Then we can think about cube root, the entire cube root of xy squared and xy squared. We can recognize that as a common factor. So the derivative law says we can just simply add. So coefficient 1 plus with coefficient 4, and we multiply that with the 1 common cube root of xy squared. And 1 plus 4 will yield that final result, 5. And that's how we ended up, once again, 5 cube root of xy squared.